Share the screen. Where you at? There we go. All right. Welcome to chapter 13, Running Water. This is for the geology class at Go Gibbet Community College. And let's begin. Earth as a system, the hydrologic cycle. You've heard of the hydrologic cycle before. It is the water, the hydrosphere we've talked about before, the water on the Earth. The Earth is unique within the solar system itself because it is the right distance away from the sun, from the heat of the sun, and the right size, the right gravity to have liquid water on the surface. And you also have mantle convection, which we've talked about previously, that can bring water to the Earth's surface from down below. So the hydrologic cycle describes the movement of Earth in relation to the Earth's four spheres: the geosphere, which is the geology, the hydrosphere, which you're going to talk about this chapter, the atmosphere, which is the gas, what we breathe, and the biosphere, which is us. Picture of the hydrologic cycle. You talked about this in middle school science class. I'm sure you very well about the precipitation, runoff, evaporation, turnabout that goes down. As I'm sure we are all well aware, the vast majority of water on the Earth is in fact salt water in our massive oceans. Of that water, about 2.5% of it is actual groundwater. And of that groundwater, the vast majority of it is in glaciers or, well, groundwater. So 2.5% is freshwater. So the actual surface freshwater that we drink that are in our lakes is about 1.3% of the 2.5% of the total amount of water on the Earth. Not a whole lot of the Earth's water is usable without having to go through steps. However, this chapter isn't about water, it's about running water. Specifically, let's talk about streams. A stream we're going to define as a channelized flow. Water flowing in a channel. A river we're going to call a large stream. All right? So a couple of definitions for you. A river is just a big stream, and a stream is any flow of water that follows some sort of channel. You have drainage basins. These are areas of lands whose surface runoff feeds the stream. So this is everything before the stream head, right? The divide, or the imaginary line separating one drainage basin from another. It says imaginary line, but this essentially says, is the water going to go to this stream or that stream? Let's draw a line where that separation occurs, right? This is sometimes visible as a high ridge in a mountainous region. They can be very hard to determine most of the time, and continental divide splits a continent into different drainage basins, which we'll talk about. There's the divide there on the top of this hill. If you flow to the left or the right, the water that flows down is going to feed different rivers. So this drainage basin here in the center, all the water that lands in this particular basin, all will flow into this one stream down at the bottom here. The couple terms for you: headwaters is the upstream portion of the drainage basin. The mouth is the end of the river. So right here, the river goes into the outlet, or the stream goes in the outlet. That's the mouth. And the tributaries would be all the feeds, all these blue lines on this hill here. All these feeds are called tributaries. Yellowstone would be a good example of a drainage basin. If we look up here, the Mississippi River has a massive drainage basin. That looks to be about half of the continental U.S. all eventually feeds itself into the Mississippi. Within that massive drainage system, of course, we have many sub-drainage systems. The Arkansas Red White, Lower Mississippi, Upper Mississippi, Ohio River Basin, things of that nature. Within these individual river basins, these all feed into the same total river. You can zoom in further to the Yellowstone River drainage basin. These have many tributaries that tie together into the Yellowstone River. And the Yellowstone River itself is, in fact, a tributary eventually to the Mississippi, but if it's large enough, we call it a river anyways, right? The Bighorn River feeds into the Yellowstone, yes, but the Bighorn River itself is also an important river with its own tributaries. So, rivers or stream systems. We're probably going to say river a lot because that's what you picture when I talk about running water, not necessarily a stream. So, it's fine that we're going to go back and forth there. River systems drain most land areas of Earth, with the exception, of course, of extremely arid or polar regions. We can divide river systems into three separate zones: sediment production, sediment transportation, and sediment deposition. Sediment should be familiar. We've talked about that in previous chapters with sedimentary rocks. Here are the three zones of the river. The zone of sediment production is in the headwater section, the tributary section, wherein the smaller streams collect the water that eventually condenses into the main river, giving you, and it's bringing along all those sediments along with it. The mountain is eroding essentially along these tributaries and rivers. Zone transportation is mostly movement of the sediments from the mountain, and then the zone deposition will be the delta wherein, or the mouth shown here, wherein the river eventually deposits into whatever it's deposited into, be it another river or be it a lake or an ocean, something like that. Notice the mouth of the river itself widens out at the end because that is the deposition of those sediments. Sediment production, zone where most sediment is derived. Most, not all, keep that in mind, sediment is always uptaken by rivers throughout their process, but the majority of that sediment comes from the sediment production zone. Located in the headwater region of the stream system, talked about that already. Where's the sediment coming from? Mostly bedrock broken into smaller pieces. That's probably going to be a big part of your sediment production. Some bank erosion, sure. Bank erosion, however, goes throughout the river process. Scouring of the channel bed. Yep. And stream cross sections. Then you get to your sediment transport section. This happens when, as I said, all that sediment taken from the head flows through. Some of it's deposited, most of it's carried. Lastly, you get to sediment deposition. This is your basins, this is your gulfs, this is your mouths, where the water slows down as it reaches the larger body and deposits sediments. Only very fine sediments actually reach the oceans because most of them are deposited as the river slows. Water moves in a river channel under the influence of gravity, right? Water flows downhill. Within that, you can define more or less two different types of flow. You can have laminar flow, which is slow, and turbulent flow, which is fast and erratic. Picture of laminar flow here. This is any slow-moving river. You got to look at it. You don't only hear the river moving. You got to look at it to see it moving. Kind of almost looks like a lake sometimes. Up here where the local class is, the Copper Country extension of Gogebic, we have the Portage Lake. It's called Portage Lake, but it's actually a river because it moves so slowly, you don't see it moving. It's a laminar flow system, but the Portage Lake, the Portage Canal that is cross-cutting Hancock and Houghton is in fact a river connecting to Lake Superior. Turbulent flow is turbulent, right? This is what you do. This is where you get your white water rafting. This is fast, exciting rivers. I should also add, turbulent flow does not always look like this. There's not necessarily, well, I think there is a strict definition to separate these, but we're not going to get into that in this class. Laminar flow is slow, turbulent is fast. That's plenty enough information for you. What affects these stream flow velocities? What turns a laminar into a turbulent flow? Well, slope or gradient, first of all. The steeper the slope, the faster the water moves, right? Channel shape is also a big part of this. The wetted perimeter, the area where the river is in contact with the channel. The most efficient channels have a small wetted perimeter compared to its cross-sectional area, meaning a narrow, deep channel that has a small wetted perimeter, less frictional drag, and will flow more efficiently, right? Your narrow channel is down below there, whereas your wide channel is up on top. What's going to flow here? Which of these is going to flow fastest? Which of these is going to take up the least amount of wetted perimeter, right? These both have the same cross-sectional area, 10 units, but the wetted perimeter itself is 12 for the wide, 9 for the shallow. Sorry, 9 for the narrow. Meaning you get a darker blue there in the center, as you saw there, for a faster maximum flow. Channel size and roughness also obviously can create and affect flow. A rough channel full of, say, boulders and things like that create turbulence, lower total velocity. Discharge, well, that's obviously a big one, right? The more water you have coming in, the faster water is going to flow. When discharge increases, width, depth, and flow velocity will also increase. The USGS, the U.S. Geological Survey, monitors stream flow, velocity, discharge, and river stage to have a better understanding of what's going on with water flow. It's a very useful data set for resource management. Shown here is a picture from 2012 of the USGS and all these streams it watches and all the stream flows it pays attention to. It's important to know when stream flows are low because that tells you how larger rivers are going to be affected. If you have a lot of low stream flow in a time when you wouldn't expect low stream flow, then that's going to cause the rivers that are being fed by these streams to therefore be smaller and can have a major impact on agriculture, trade, industry, things of that nature. You can take these ideas and put them into what's called a hydrograph, as shown here. As you can see, this hydrograph describes precipitation, storm flow, discharge, things of that nature. So you have a rainfall event, and when it gets done rainfalling, the discharge itself will increase up to a certain point and then will fall or regress down again. You get a lot of rain, you get a lot of discharge. The angle, the slope of these limbs can play an effect into things such as flash flooding, things of that nature. And the height of it overall is something that is very important, as I said, because if you don't get a lot of discharge, because you don't get a lot of rainfall, you lose water. Changes downstream. How can downstream rivers change? Well, we can talk about the longitudinal profile, or the cross-sectional view of the stream from the head to the mouth. The head, of course, would be the source, and the mouth would be where it empties. Most longitudinal profiles have some sort of concave shape to them, where discharge increases towards the mouth, and channel size and velocity often also increase towards the mouth. So rivers start out thin and widen out. If you've ever been to, let's say, the Mississippi, you know the Mississippi River is huge, especially down south around, well, Mississippi. However, if you go up very much north to some of its feed rivers, those rivers are a lot smaller. Here we can see that longitudinal profile relating elevation to distance away, right? Here's the Kings River in California, draining off of Mount Whitney. This, I think, does a better example of explaining this concept. As your channel slope decreases down, your discharge amount increases and your channel size increases, vice versa. Most channel roughness and channel slope are similar to each other. Flow velocity slowly increases as you get going down because all this water is rushing down, collecting with itself. All these tributaries up in the mountains have very steep slopes, very steep, very rough amounts, but they don't move that fast individually. However, when they all collect down into the river itself, the flow increases eventually, until it hits a certain point. The channel size increases eventually, and the amount of water flowing through these parts increases. So when you get to the mouth at the end, you have very large deltas, very large rivers, a lot of water, a lot of sediment flowing through. Erosion. Water causes erosion, right? We are well aware of this. Erosion is related to the slope, discharge, and bank bed sediments that will possibly be eroded. Sand is easily eroded. Silt and clay-sized particles are harder to erode. Quarrying is what we call the removal of large blocks from channel beds. Stream erosion can have an abrasion component to it, where sediment is broken down and polished by scraping, bumping, and rubbing. Potholes can form, actually, if you ever go out walking around a river that is going through bedrock, you'll see potholes. We'll show that in a bit. That is something that can be developed through the bumping, scraping, and rubbing of sediment in a particular location. Corrosion occurs when material gradually dissolves in the flowing water, for example, limestone. Here's an example of some abrasion potholes, and these are developed by water flowing in here, sediments being stuck, tumbling around, slowly breaking and cracking what the rock that is the surrounding bedrock. These are naturally found. If you notice, the stones within these are also themselves going to be very smooth because they keep getting tossed around a lot. So, all streams, by definition, transport sediment. There are many different ways, however, for this sediment to be transported. We can talk about dissolved loads in solution, suspended loads, which are in suspension, or bed loads, which are rolling or sliding along the bottom of the riverbed. Pictured here, I think, very well. Your dissolved loads are, well, when it's dissolved, right? When you dissolve sugar in water, you don't see the sugar anymore. A suspended load would be your muddy-looking water, your silts and your clays. And, of course, your bed load is everything on the bottom, all the bouncing, sliding, rolling boulders, sand, and gravel of the riverbed. Yep, dissolved loads, water dissolved in, doesn't affect stream velocity. Suspended loads, however, are not dissolved in and have a interesting component to the velocity of the water, that is the settling velocity, or the speed at which particles fall through the still liquid. The suspended load, that the sediments being carried by the water are still affected by gravity, they're going to eventually fall, but not too fast. The speed at which they fall, of course, depends on the size of the material. Notice here, settling velocity increases the coarser the material gets, the larger the grain sizes get. Above the same velocity, the thing is transported. Notice right around here, there is no deposition for very tiny clays and silts. That is because these things are carried basically indefinitely and eventually will usually dissolve into the water. Larger grain sizes eventually deposit because they're heavy. If you get a muddy-looking river, that's because of a large amount of suspended sediment involved in the water. This is usually something that is filtered out as the river travels. Notice, again, this is in the mountains, right? This is in rough landscape. So this is probably not a large river. This is rather a more in the mountains, in the hills, tributary feed system. So this sediment is probably pretty fresh in that river. And bed load, as I said, this is the riverbed, the moving of rocks and particles on the bottom. Couple terms to care about for running water: capacity and competence. Capacity is the maximum total load of solid particles the stream can carry. Greater discharge, of course, greater capacity. And the competence is the maximum particle size that the stream can transport. Faster streams have higher competence. So these describe the sediments involved in the moving water, how big they are and how much it can carry. This deposition, of course, occurs when the stream's velocity is less than the settling velocity. We talked about that before, and particles eventually settle out. gravity pulls the particles down. The particles stop moving because the river's not strong enough to move them, right? Larger particles settle out at higher velocities. Smaller particles settle at lower velocities. And you eventually produce what's called a alluvium, which is a sedimentary deposit by stream. As the water travels, as we said before, it's going to call out whatever it wants to because it's a river. You can't stop it. You can create bedrock channels, which is when a river is cut into rock. These often form in the headwater region where streams have a steep slope. You can find your potholes, pools, steps very commonly in here, and the channel pattern is actually controlled by underlying geology. Wherever the rock is softest, the water is going to cut through, create channels, etc., etc. And of course, you have alluvial channels. These are channels formed in sediment that were previously deposited by the river valley. These are your floodplains. These channels can change shape as materials erode and transported through. This alluvial channels give you meandering channels. Again, this is something that should seem very familiar from middle school science. Meandering channels are stream transport sediments in broad sweeping bends called meanders, meandering around, right? Meandering channels, of course, evolve over time. Outside of a meander, you have a zone of active erosion. Inside a meander, you have a zone deposition. If that doesn't sound familiar, when we get to the picture, it'll make more sense. Through times, the bends change as the outside of a bend erodes away and the inside of a bend deposits, and eventually they get cut off and form oxbow lakes, right? Down below here, we have good examples of this. This channel, this white river in Utah is meandering around, and on the outside of a meander, you're eroding the soil, as shown in this picture of this house that I feel bad for. And on the inside, you get these nice little point bars, these nice little river beaches, because that is where things slow down and you have deposition of material, right? Slowly meandering. Eventually, as shown in this picture, the meanders will get too extreme and will actually connect with each other, as shown on the left side of this Wyoming river picture, where the river itself was meandering all the way back around, but it cut itself off, created a new channel, leaving a lake to form. And if we look backwards in these, if we look up in this picture, we can see many oxbow lakes actually have formed because the river got so tight with its curves that it flowed over itself. So I think in here, in this picture, there's 1, 2, 3, 4. I count 4 oxbow lakes. There may be more. You also have braided channels. If something is meandering, it's probably braided. This is a network of converging and diverging channels that flow among numerous islands or gravel bars. Large portion of the load in these braided channels is coarse, and baked material, of course, is easily eroded or reworked. Here is an example of a braided stream. There is no predominant path, or whatever predominant path there is not so predominant that all the water flows through it, and the stream braids out and kind of looks like someone laid their hair on the ground here, right? All these individual channels in amongst themselves are meandering around, but the total flow of water covers a very vast space, not just one individual channel. Stream valley, this is, well, the channel of the terrain that the water cuts through, right? Alluvial channels have very wide valley floors. Bedrock channels have very sharp V-shaped valleys. Here's some bedrock channel. Notice the valley wall, the very dense V shape. This is in Yellowstone, seen here. And you can see the rapids. And what this is over time, this river has been cutting this V down into the bedrock. At one time, it was higher. It was probably thicker, slower, but time takes its course. You can't really stop a river, right? And it digs it deeper and deeper and deeper and faster and more vigorous down cutting. As shown here, you start out with your narrow V-shaped valley. Eventually, things erode away. Things start to meander. You get a nice floodplain, maybe some crops, things of that nature, some lakes, places like that. The natural path rivers tend to take, especially if they go through mountainous regions. Remember, when it says time, you're in geology class here. This is a geologic time scale. This is a very, very, very long amount of time. We're talking millions of years, tens of millions of years, something along those lines. Talked about deltas a lot. Let's go into some definitions. A delta forms when sediment-filled streams enter large bodies of water. The stream's forward velocity is decreased, therefore decreasing the carry capacity. And if you decrease the carry capacity, the sediments fall out, creating a delta. The main channel divides into several small channels in the delta called distributaries, because they distribute the water, distribute the sediment. Shown here is said delta. We can look at the bottom here, a time lapse of the development of the delta as the stream enters this larger body of water, this lake, this ocean perhaps. It brings with it its sediment. As it keeps bringing it, the sediment is deposited more and more and more, and the river, which was once a single river, starts to braid out and develop into many rivers as it keeps depositing material because the river itself slowed down. Of course, the Mississippi River Delta is a fantastic example of this. It's a series of 7 coalescing deltas all across the end of the Mississippi, and river today is trying to change course to a different river. The river abandoned its current course as it goes to New Orleans, and engineering is trying to prevent this mitigation as much as possible. Right? As shown here, the Mississippi River, dumping in the Gulf of Mexico, has many different paths it takes to dump its water, dump its sediment. This entire basin here was developed by the Mississippi. All this sediment down here was developed via these mechanisms we've been talking about. And you can see up here at the top here, they're trying to keep the Mississippi where it's going instead of pathing out, because that can cause a lot of issues for towns and cities that live on the Mississippi. If the Mississippi decides to change course, you don't have the access to the same amount of water that you once did. That's not a good thing. Natural levees. Natural levees are raised areas adjacent to the channel that form during flood events. The levees. They keep water in the channel, and following floods, they prevent water from returning to the channel stream, creating swamps, things of that nature. Right? So you have this river shown here. This riverbed is developing sediments on the sides. It overflows. Post-flow here, you have these coarse sediments creating a levee such that the water has a harder time going in. This levee is dry, they get hardened. So the next time flooding occurs, the levees continue to grow, keeping the river basin set and keeping the water in the river for longer, so that it takes more water to flood to blow up these areas, blow up these regions. Alluvial fans. I think we've talked about these before. I can't quite remember. These are fan-shaped depositions of sediment at the base of mountain fronts. Streams tend to emerge out of these into the flat lowland, and they kind of look like fans. This is sediment falling off of the mountain, being carried sometimes by the water. There's pictures in Death Valley, as you can see. And it just looks like someone fanned a bunch of sediment out off a mountain. Floods. I'm sure are aware of floods. Floods are dangerous. Every single stream will flood, because the river has a certain height to its bank. If you get more water than it's accustomed to, the water has to go someplace, right? It will flood in many different ways. Regional flood, a flash flood, an ice jam flood, a dam failure flood, perhaps. These things all happen at all water sources. Regional flooding, of course, is a seasonal event, and it results from spring rains or rapid snow melting. In 1993, the upper Mississippi flooded and caused some damage, right? Flash floods are not seasonally dependent. They occur more or less without warning and can be very catastrophic. In August 2011, a flash flood occurred in New York and Vermont from Hurricane Irene. The water just overflowed its banks, caused major amounts of damage. 2,000 road segments were damaged by this flood. 800 homes and businesses had issues, things of that nature. The stream rose 14 feet in less than a day and then subsided quickly, and when that rose 14 feet, what happens there is water has to go someplace, right? Up here in the Copper Country, we had the Father's Day flood. Same events happen. Flash floods, again, the difference between a regional flood and a flash flood mostly is that regional floods are seasonal. You kind of know when things are going to flood and you can work yourself around it. Skipped a few there, sorry. A flash flood happens in a flash. Ice jam floods occur when you have an ice dam that is broken, more commonly occurring where you have large amounts of ice. And of course, if you build a dam, for example, usually a human-made dam, but sometimes natural dams, when those break, things flood, right? Here's an example of an ice jam break here. And here's a dam that loosed and flooded. Dam held back a bunch of water. Water's got to go somewhere, right? So, flood controls. What can you do to mitigate these issues? You can't do the same thing with earthquakes and all these geologic events. You can't really stop what's going to happen as much as you can try really hard to prevent it, right? So, flood types and controls. We have artificial levees. We talk about natural levees. We can make our own levees, right? Earth mounds or concrete walls built on river banks to increase the capacity of the channel. These fail during a flood because you can only build them so high, really. You can only spend the money to build them so high, and the water is going to always be larger. You can channelize a river to create alternate streams for the water to flow. However, if the more streams you create, the more erosion you have, and that brings about its own problems. You can build dams to store this flood water and release it slowly, but again, dams fail. And there's also non-structural approaches. The best approach to flood control is to simply limit the amount of development on floodplains. If you know something's going to flood, don't build there, right? But floodplains themselves are usually very fertile, very flat, good places to build usually, outside of, floods. So yeah, that's the end of this chapter. Pretty short one overall. Interesting topics, right? If you live anywhere near water, flooding is something that's going to happen. How often and how large, it's completely dependent on what the earth feels like doing that time. As said before, these questions are for you to check your information. Feel free to pause at any moment to go through the question, figure out the answer. If you can answer these questions, you can probably do the assignment that will be assigned along with this chapter. And if you don't feel these are helpful to you, well, you don't technically have to do them. They're for your benefit. Thanks again for watching this chapter. I hope it helps you. Stay safe out there, and I'll see you in the next chapter.